Okay, here we go. Ready. Back to continuous random variables. Okay, so last time we were talking about continuous random variables in contrast to the discrete random variables we had before. So the range of a continuous random variable is an entire interval, possibly infinitely long. And instead of a probability mass function, what we have now is a density function. And the probability that we get an outcome, say in the interval from A to B, is obtained by integrating the density function. Where little f is the density function. And we, as before, we have the cumulative distribution function. Capital F, the probability that we get a measurement x or smaller, well, that's like this, but without the a. So we're integrating from the bottom, minus infinity, to x. And we integrate the density function. And little f and capital F are related. The density function is nothing but the derivative of the cumulative distribution function by applying the fundamental theorem of calculus to this equation. Well, that's where we were last time. Let's try to see what the density function means. Well, it's a little imprecise what we have in mind, but let's draw the picture. Suppose we have a density function whose graph looks like this. Say the density is 0 for a while. Well, then maybe it goes up and down. Well, so that's telling us that there's no chance, that a 0 probability of getting a measurement of -5 out here in the graph. So there's no chance x is near here. The density is large here. That's telling us that there's a large chance that we get a measurement x near here. Whereas when the density is small, yeah, x might be there, but there's a small chance that x is near here. Well, where this is the graph of the density function. Well, that's a little hand-wavy. Let's try to be a little more exact. Suppose we're interested in some point here. Well, if we look at, what's the chance that we get a measurement near here, where near, say, is between x and a little to the right of that, between x and x plus delta x. Well, so we could look at that, almost a trapezoid there, that blue region. F of x is roughly well, what it is exactly is sort of the height on the left edge here. That point on the curve is f of x. But that's roughly the shaded area divided by the base. Well, that shaded area is the probability that we get something between x and x plus delta x. So let's write that down. We get, let's write the capital X so we can make sure it looks different from the little x. Well, it's an approximation because this isn't exactly a rectangle. But for small delta x, this height f of x will be roughly that area divided by the base. So it's, we can think of it as it's probability per unit area. Probability per unit length, not area. It's the probability of being in this little interval divided by how long that interval is. A probability per length. So that's what's sort of what we're saying over here. Where the density is small, the probability per unit length here is small. Well, but let's try to do something more exact than drawing these pictures. We need equations for the expected value and the variance and so forth for a continuous random variable. So I want to put down 3 or 4 equations here. For the expected value, or the mean, I claim for a continuous random variable is going to be given by integrating x times the density function. And we integrate it over everything. And the reason, well, back for the discrete random variables, we had a sum, right? A weighted sum. Took what the values of the random variable weighted by the appropriate probability. And the same ideas are involved here. The reason this formula applies, well, this is not a rigorous proof, but it gives an idea of where it comes from. I'm just going to look at the case where we don't have an infinite interval where the range of the random variable is, suppose it's just a closed interval from A to B. So that A and B. So the density is going to be 0 outside this interval. And then, well, we don't know what it does, but there's no chance of getting something outside the interval from A to B. And what if we wanted to get an idea of what the expected value is? We can get an approximation if we partition that interval into lots of little parts. Say n equal parts, each of length delta x. And we'll choose x sub I in the ith piece of this partition. So x1 is going to be near A, and x sub n is going to be near B. And x sub I is out here in the middle somewhere. And we're going to look at that ith piece of this partition. We have this subinterval here from x sub I to x sub I plus delta x. Now, what about the expected value? Well, we could get an approximation to it by looking at, well, the values the random variable could take, weighted appropriately, and then we add them up. What if we take x sub I, weighted with the right probability, the probability that we get something between x sub I and x sub I plus delta x? Well, that probability is about f of x sub I times delta x. And then we will add these up. That is, what I'm trying to do here is take the values that the random variable might have. Well, it could be anything in this interval, but we'll break the interval into lots of pieces, and it won't change very much, we're supposing, in any one tiny piece. And then we'll weight that with the probability of getting something in that little piece. So we get this weighted average of the values weighted with the right probability. But you look at this, and of course, it's a put-up job. You've seen this before. This is nothing but the Riemann sum, right, from talking about integrals. Now we take the limit as n goes to infinity, so that this will converge to an integral. Converges to, as n goes to infinity, the integral of x times f of x dx. The equation for the mean of a continuous random variable. In fact, this is to help remember it, we're taking the value or values that the random variable could have. We're weighting it with the appropriate probability. F of x dx, well, it's what you get in the limit from the f of x times delta x. And then we add them up. Well, that's what this says to do, and in the limit, of course, we do it by the integral. Well, that's where this comes from. Now what about the variance? The variance for the random variable, well, there's no change in the definition. It's the expected value of a related random variable, namely x minus mu quantity squared. This is the same as before, right? But the expected value now is, of course, an integral. X minus mu squared is this other continuous random variable, and its expected value is, well, we integrate the various things that x minus mu squared can be, each weighted with the appropriate probability. But as before, there's another way to write the variance that's often more convenient. Okay, call this number 1. So equation 2b, the variance. It's the expected value of x squared, so that will be a continuous random variable related to x, but different, minus the square of the mean. And the expected value of x squared, well, by the right-hand board, we integrate x squared, weighted with the probability. And finally, just to complete the list, of course, often what we want is not the variance. We want the standard deviation. So we take the square root. Well, so it's a combination of things that we had back in section 12.4, but some things are new, because instead of those sums, we now have integrals. The limit of the Riemann sums. Well, let's work a problem. For the uniform distribution, say we assume that the random variable x has the uniform distribution on the interval from 2 to 4. That means that the density function is 0 outside this interval. There's no chance of getting a measurement outside the interval from 2 to 4. But it's constant. The uniform part of the uniform distribution means it's constant between 2 and 4. And what is that constant? Well, it has to be a half if for this interval of length 2, so that the total area under the density curve will be 1. Right? The density function has to integrate to 1 when you integrate it over the entire real line. So if this had been an interval of length 3, the constant would have been 1/3, and so forth. Well, what's the expected value? Well, we're going to give it a fancy treatment, but if you'd guess, you'll be right. Okay? What would you guess? 3, of course, right in the middle. The expected value should be the average measurement, and if it's uniform from 2 to 4, the average should be right in the middle. But not being happy with that, we're going to do it using this equation. So we need to integrate the density function times x over the entire real line. And the density is 0 except from 2 to 4. So we're just integrating from 2 to 4, x times a half right. The half, it only applies in the interval from 2 to 4. The density is 0 elsewhere. Okay, so we do this integral. We need an antiderivative, like x squared over 4, which we evaluate between the limits of integration. We have 16 over 4 minus 4 over 4, 4 minus 1. Yep, it's 3. But we want the variance also and the standard deviation. Well, for the mean, I said, of course. There is, for the variance, we don't have I don't think it's obvious from the picture what the variance is going to be. So we'll work it out. First, let's calculate the expected value of x squared. Okay, so we have to integrate x squared times the density. Well, so the density is 0 except between 2 and 4. So the only non-zero part of this integral will be the part between 2 and 4. Well, so we need an antiderivative for x squared over 2. Let's use x cubed over 6. Four cubed is, well, that's 64. 2 cubed, that's 8. (28 over 3), a little more than 9. But we want the variance, and this is the expected value of x squared. So the variance will be the expected value of x squared, this 9 1/3, minus the square of the mean. Well, the mean was 3, so we square it. So the variance of this random variable is 1/3, and so the standard deviation is the square root of that. Well, let's find the probability that this random variable is within one standard deviation of its mean. Well, the mean is 3. So we want the probability that we get a measurement that it's at most 3 plus 1 standard deviation and is at least 3 minus 1 standard deviation. Well, so we could, it's an integral, but since we're integrating a constant function now, and right in the picture, we're finding the area of a rectangle. There's the mean. 1 over the square root of 3 is between 0.5 and 0.6. So yeah, 3 plus 1 standard deviation is like there. 3 minus 1 standard deviation is there, and we want to integrate. So we want the area of this rectangle. So instead of doing the whole integral bit, let's just use base times height. The base of this rectangle is 2 over the square root of 3, and the height is 1/2. Yeah, so the probability of being within 1 standard deviation is, again, 1 over the square root of 3. And numerically, if we ask our calculator what that is, to the nearest percent, it's about 58%. Now let's focus on a particular sort of density function and talk about the exponential distribution. One of our 5 or 6 or 7 distributions, I guess it's 7, that we talk about in this course. So one of them is the exponential distribution. But actually, we talked about this last time, but not by this name. I mean, suppose, going back to things we were talking about last time, suppose we have a Poisson process. So hits occur now and then at random, independent of the past, but with a known long-term average rate. Rate lambda, hits per unit time. And the Poisson distribution would let us find the probability of getting some particular number of hits. But instead of looking at number of hits, we looked at the random variable L for lifetime, the time you have to wait to the first hit. The time from when the experiment starts, but the Poisson process is independent of the past, so you could start it anywhere, until the first hit. So let's look at this, and in particular, let's look at its density function. Well, first, the probability that the lifetime is more than some time value is the probability that the lifetime is more than 100 years means that in the first 100 years you don't get that first hit. There are no hits in the first 100 years. And the Poisson distribution says that probability is e to the minus capital lambda times 1, right? Lambda t to the 0th power over 0 factorial. So the probability that L is less than or equal to t, that's the complement of that. And this is nothing but the cumulative distribution function. So the density function we can get by taking the derivative of this. The derivative with respect to time of this, well, the derivative of 1, that's just gives us 0. Okay, the minus lambda comes down, so we have a minus lambda, plus lambda, e to the minus lambda t. Now this is only applicable from time 0 on up. It makes no sense to get the first hit in negative time. And the graph of this density function well, it's an exponential function. When t equals 0, the density is lambda. And then it decays exponentially. It never gets down to 0, but it approaches 0 as a horizontal asymptote. Now, in general, any random variable that has a density function like this is said to be exponentially distributed. Well, so let me write that down. So a random variable, say x, we'll say is exponentially distributed or has the exponential distribution with parameter lambda. Lambda has to be a positive number. It can't be negative. I mean, you know, the area under this curve is 1, but if lambda were negative, it would be a very different situation. Lambda some positive constant. If it has that density function, lambda e to the, well, should we use x or t? Doesn't matter. In the applications, the variable is often time. As here, and when it's time, we'll want to use the letter t, and if it's something else, we want to use some other letter. And so some applications of the exponential distribution. Well, there's one we know so far. The time to the first hit in a Poisson process. a very different sort of application, which you'll read about in the book. Example 17. Applies the exponential distribution to dispersal of seeds. In this case, x is not time, it's distance, the distance that the seed lands from the parent plant. Well, that's rather different, or at least it appears rather different from a Poisson process. We'll also apply it to the lifetime of an organism. Where we ignore aging. That is, it applies to an organism in which old age is not a significant reason for dying, because there are more immediate risks like injury or infection or probably getting eaten by a predator. Where we get to ignore old age, well, that's actually similar to application 1. Getting eaten by a predator might be thought of as a Poisson process. I mean, that predator might appear most any time. And that first hit is when the organism gets eaten or suffers some fatal accident or gets some fatal infection. Well, we've talked about mean and variance of continuous random variables, and we've talked about the exponential distribution. Time to put those together. Okay, so for the exponential distribution, okay, so let's I'm going to call the random variable L instead of X, so again, we'll think of it as being like a lifetime, but it's just a random variable with the exponential distribution. So there's some parameter lambda, some positive number that tells us what its density function looks like. And we want the mean and variance and standard deviation. And we expect that these will depend on what lambda is. Well, we know how to start. The expected value, the mean. We have a formula for it. We want to integrate, I'm going to use t instead of x, because thinking of it as time. We want to integrate t times the density function over everything. And here's the density function. Okay, so we'll plug that in. So the density is 0 for negative time, negative values of t. So that lambda e to the minus lambda t doesn't apply until we get up to time 0, and then it applies from 0 out to infinity. So we have t times the density, lambda e to the minus lambda t. and we want to evaluate this integral. Okay, step 1 in the evaluation. We need an antiderivative. For t times lambda e to the minus lambda t. Just the indefinite integrals. We just need an antiderivative. Well, back in 3b, you were a whiz at this. Time to do it again. You look at that and you say, aha, we've got to use integration by parts. There's nothing else that'll work. We know how to integrate e to the minus lambda t. In fact, we've been doing that before. And then we can differentiate away the t. Okay, so we know an antiderivative for e to the ax, 1 over a e to ax plus c. We've said that before, and we need it again. So t times, okay, so we're going to split the integrand here. We're going to integrate the thing on the right and differentiate away the thing on the left. So first we got to integrate that. Well, so we get a minus 1 over lambda. Okay, the 1 over lambda part cancels with the lambda we got. Yeah, so we get the antiderivative minus e to the minus lambda t. Minus, okay, now we get to differentiate the t. Okay, that just gives us a 1, which we don't even need to write down, times this integral here, minus e to the minus lambda t dt. So this is now a plus sign. Okay, so we've got that first term here. And now we have to do the second integral. Yeah, but this we know. We know it because it's this. So we have a minus 1 over lambda e to the minus lambda t. So here's our antiderivative. That's the end of step 1. On to step 2, we'll integrate it. Well, we'd like to integrate it from 0 to infinity, but first we'll just integrate it from 0 up to some number, say b, and then in step 3 we'll take the limit as b goes off to infinity. Okay, so we'll take our antiderivative that we found here, which was minus t e to the minus 1 over lambda. Okay, we'll take the constant to be 0. And we get minus b e to the minus lambda times b minus lambda e to the minus lambda b. And then we plug in t equals 0. Well, so this first term just gives us 0 times 1. So minus 1 over lambda times e to the 0. Step 3. We want the improper integral, 0 to infinity. So we need to take the limit as b goes off to infinity to get the integral that we're after. Well, as b goes off to infinity, we'll look at each of these three terms here. 1 over lambda is a constant. It doesn't depend on b. So its limit is itself. What about e to the minus lambda b? Well, we can think of that as 1 over e to the lambda b, and lambda is positive. So as b goes off to infinity, lambda b goes. Okay, lambda times b is going to go off to infinity, plus infinity. So what happens to e to the lambda b? Well, as that exponent gets larger and larger, e to the lambda b goes off to infinity. The exponential function for a positive number lambda would look like this. And we have 1 over that. Conclusion, e to the minus lambda b is going to 0. That leaves us with one more term to handle. So we have that b times e to the minus lambda b. Well, think of that as b over e to the lambda b. And we look at this limit as b goes off to infinity. Well, the numerator is going off to infinity, and the denominator is also going off to infinity. So we have an infinity over infinity limit. We do it the usual way. We apply L'Hopital's rule, which is the only way to evaluate this limit. So this has the same limit as, it's not equal to, but it has the same limit as, so we'll use this little squiggle like this. And then we take derivatives with respect to b, the thing that's going off to infinity. So the derivative of the top is just 1. And the derivative of the bottom, well, lambda e to the lambda b. But we know the limit of this. It's 0. This goes to 0 as b goes to infinity. Conclusion, putting everything together, the integral from 0 to infinity, t lambda e, is the limit of this as b goes off to infinity. That first term goes to 0. That second term goes to 0. And that third term converges to, in fact, it always is, 1 over lambda. So the mean with the exponential distribution is 1 over lambda. Well, think of it in terms of waiting time for the first hit. If lambda is big, that means you get an awful lot of hits coming in. You don't have to wait very long. The waiting time would be short. Where if lambda is very small, if there's hardly ever a hit, you expect to wait a really long time for that first hit. Okay, well, we will do the variance and the standard deviation some other time. Got to stop.